All right, hello, and welcome to Microchip's Meet the CLB live stream. In this live stream, we're going to be looking at Microchip's latest peripheral on a PIC16 microcontroller, the Configurable Logic Block. In the next 45 minutes, we're going to prove why adding the CLB to your next design can make it faster, more efficient, and especially reliable in safety-critical applications. I'm joined today by some very special guests. At the end of the table is Clifford Swartz, and next to him is Ulysses Iniguez. They are our CLB experts, and they will be building a demonstration live during this live stream.
Good morning, Josh. Happy to be here.
Thank you for joining me. And then sitting next to me is Patrick Marcus of Marcus Engineering. He is an industry expert. So Patrick, will you give us a little bit of introduction on Marcus Engineering and yourself?
Yeah, thanks, Josh. I appreciate being here. I'm Patrick Marcus, the president of Marcus Engineering. We've been a premier design partner for almost 15 years now. We are an engineering design consultancy out of Tucson, Arizona, and we specialize in heavily regulated products, including medical devices, military, and aerospace applications. And I'm really excited to hear more about the CLB and see how it might be able to help us out.
Great, that is exactly what we want to educate people on, is how the CLB can help them. The CLB is a configurable logic peripheral, kind of like a small FPGA on a PIC16 microcontroller. Now, we're going to be talking to a wide range of audience members here in this live stream. First, we're going to be talking to microcontroller experts. Those are people who've used PICs, AVRs, ARM cores in the past, who tend to want to just use a microcontroller for their projects. They may know they have needed an FPGA or programmable logic device in the past, but they've always seemed too daunting to approach. We believe the CLB solves that problem by being the easiest way to get into programmable logic anywhere. I'm also going to be talking to CPLD and FPGA designers who have not really used microcontrollers in the past. When we look at the market that the PIC16 F13145 family exists in, which is the microcontroller that has the CLB, we're going to see that it can function as a standalone PLD very competitively, even if you don't want to touch the microcontroller aspect of the design. And then lastly, we're going to be talking to participants and potential participants of our 2025 Configurable Logic Design Challenge. This is a design contest that Microchip is hosting in the spring of 2025. It's going to start in March. We're going to have 2 months where participants can submit ideas for their CLB designs, and then we will provide you with development tools and some hardware to build your design into a video. When you submit your video, we will pick winners of who we think is the most innovative and creative use of the CLB, and we are giving away up to $10,000 in prize money. We hope this live stream can inspire you with potential ways to use the CLB, and we want to give you a jump start by building a live demo so you can see how to use the toolchain, and you'll be able to hit the ground running. So that's a quick note on nomenclature of who we're speaking to, and without further ado, I'd like to dive into what is the CLB. I just previously mentioned that the PIC16 F13145 microcontroller family is the most recent microcontroller that includes the CLB on it. It's the first of its kind, and it's the standard PIC16. As you can see, it has our enhanced PIC16F core with the 32 megahertz CPU and common PIC16 peripherals from PWMs, timers, and UARTs. It also has a strong analog portfolio with an ADC, DAC, and 2 fast comparators that operate at 50 nanoseconds. But let me draw your attention to the CLB block. The CLB, like I said, is a tiny FPGA, but is different from our CLCs that we have had on our microcontrollers in the past. CLCs are small bits of logic that make up about an AND gate, an OR gate, and maybe a flip-flop. The CLB is much larger than that. It actually has 32 logic elements within it, and these can be configured to operate as any of the logic gates and be dynamically rerouted. I don't know, Patrick, have you ever had experience using the CLCs or CCLs for AVR products during your work experience?
Yeah, actually, we've used the CLCs. We haven't used the CLB yet, obviously, since it's actually pretty new. But we've used the CLCs before to do some like basic inversion, maybe a little bit of and ORs here and there. But I'll tell you what, one of the things that was always missing for us was the ability to do something more sophisticated, like an oddball serial protocol that didn't quite fit the onboard peripherals, because you guys have really great UART peripheral, you have a great SPI peripheral, but sometimes certain devices just have weird things like an extra couple of bits here and there, maybe like a 12-bit serial port or something like that. And being able to deal with something like that without having to do a CPLD would have been really nice, because those tool chains for those things are ungodly painful.
Yeah, we wanted the CLB to be the easiest way to get into programmable logic. We know a lot of people have had success using our CLCs and CCLs in the past when they just need to add a little bit of glue logic. But as you saw in the 1-through-1, we just added a few more CLCs due to popular demand. Now we had 4 on the 1-through-1, but the CLB takes that a step above. Instead of being able to choose from a couple of pre-selected configurations, the CLB lets you dynamically build any programmable logic circuit you want using basic logic gates from ANDs, ORs, and flip-flops. The 32 basic logic elements are made up of a lookup table, a D flip-flop that can be used for some memory, and a multiplexer. That's standard architecture in most FPGAs and macro cells and CPLDs. So it should be fairly familiar to those dedicated FPGA and CPLD designers.
So Josh, to make sure I understand here, because I'm not really a CPLD guy, I'm more of a microcontroller guy, so just bear with me for a second. So whereas the CLC might just be good for a handful of AND gates and NOR gates and other glue logic type things, this would give me the ability to actually do like a serial protocol in hardware in the CLB and just load that data right into memory and not have to do any bit banging or anything, right?
Exactly.
Awesome.
There are ways that you can completely bypass the CPU and go pins in, perform logic, pins out without using the core at all. There are ways you can take inputs from peripherals. In fact, we'll see that later in the live demonstration. Or just use it as you would for a CLC, where you just invert it. I can do everything a CLC can do plus more.
So to make sure I understand, you're saying that I could use this logical block and not actually have to run the core and be able to like turn off the internal oscillator, for instance, and the logic would continue to run?
So the CLB would be clocked by one of the oscillators, but
yeah.
Yes, the core doesn't have to be involved at all. It can be its own dedicated logic device.
Awesome.
Yeah, even though we call it a peripheral, it can be used either as a standalone or in conjunction with the CPU, taking software in, processing it, and doing outputs. Actually, one of the really cool places we see the CLB being used is for complex interrupt wake-ups. Rather, if you need 2 conditions to be met to decide whether or not you want to take action, a lot of microcontrollers can do an interrupt on change on the pin, wake the micro, check the second condition, and if it's not met, go back to sleep. And that can add up.
So could I potentially be monitoring a serial port or a serial protocol and look for some particular data to come in and trigger an interrupt on that?
You can do something very complex like that. You could do
neat.
even as simple as just ANDing 2 signals together. We'll actually look in a couple slides of what level of complexity that can fit onto the CLB to give a better idea, a less abstracted idea of what can be done. But you're exactly right. You can analyze incoming data and just make an intelligent decision, CPU-less processing to decide whether or not to wake the microcontroller up.
And the configuration of all this stuff is like through the normal Microchip toolchain, which our colleagues here are going to show us how it all works here later.
Exactly, yes.
Okay.
We have a brand new tool called the CLB Synthesizer that is both a standalone. If you don't want to download MPLab software, it's a website, just logic.microchip.com/CLB. But it's also been incorporated into our end-to-end toolchain of MPLab so that it's very easy to get up and running. You don't have to install anything extra if you're already using a PIC16 microcontroller.
And I presume I don't have like a complex multi-day licensing process to get the tools installed like you have to do with all the FPGAs and CLPs.
You are exactly right. Yes, it is completely free.
I hate that so much. Those tool chains are god-awful.
There's no floating license. You don't have to pay per user. It can configure your bit stream to run within the CLB, and it's going to be getting a little advanced functionality in the near future, like being able to simulate a design to make it easier to run and verify what you think you're doing is what you're actually doing in the near future.
All right, well, tell me more.
Yeah, so in addition to building up that basic logic, you get a lot of the advantages with it being on a PIC16. One thing that PIC16s are known for is their wide voltage range, 1.8 to 5.5 volts continuously operating, and the CLB shares that advantage. If you want to do a battery-powered operation, as the battery voltage dwindles, the CLB can continue to operate. For a lot of programmable logic devices, you can pick either 1.8 or 3.3 or 5 volts, and then there's a narrow operating voltage. But with the CLB, you get that wide range. So especially with applications where you want to extend your power budget with doing complex interrupt wake-ups, the CLB can help a lot with that with its wide voltage range. In addition, it has a PIC16 on-chip analog that it can feed to and from. It has fast comparators and an ADC and a DAC that you can use the core to feed values into and out of the CLB. For a lot of PLDs, that's actually a continuous pain point, and it always has been. You either have to buy a separate device that has the analog on it or pay a little extra for it. But that's on the entire family has this on-chip analog that has been seamlessly integrated into the same package to interface with the CLB. We touched a little bit on low power consumption and how you can utilize that. You're only going to be drawing power consumption from the BLEs you're going to use, so smaller designs will use less power. And you have that CLB synthesizer that makes it the easiest way to get into programmable logic.
Well, I'll tell you, one of the things that really piqued my interest in what you just said was the fact that you can leverage the on-chip analog. We've only do a little bit of FPGA and CPLD work, but just trying to do basic things with those devices, and then you need some analog, you have to go through this whole extra process of adding an external analog chip. And then you have to write drivers for that analog chip in VHDL or Verilog, which is obviously a lot harder than writing some drivers for a microcontroller to talk over a peripheral. So you're having to write a driver for like an SPI bus or an I2C bus, and then you're having to write the driver for that analog element. And with this, it's all built in. And you've got the configuration tools to just kind of make those analog elements just work.
Yeah, I'm glad you've seen the pain points in your day-to-day engineering experience that hopefully this product will alleviate, that it can be this CPLD plus the analog, and you have the core there to facilitate between the two rather than you having to write specialized code just to interface them.
Yeah, certainly writing both sides of interface drivers on a regular basis every time you add a chip, it just adds dozens of extra engineering hours to things that you wouldn't otherwise have to do when things are fully integrated. So it could be a big time savings, it sounds like.
Yeah, and time savings is very important, especially for getting your product out the door. The longer it's held up, the more likely you are to stumble and want to keep chipping away and improving things, but sometimes the product just needs to ship and get out the door, and that's what we want. We want to make the development experience as easy as possible.
Time to market.
Time to market, yes, it saves money. So that's an overview of what the CLB is from a technology perspective. And now for people with a microcontroller background, let me show you a little bit of the programmable logic market. We're talking about all these programmable logic applications, but it's not always intuitive to know what you can do with what does 32 LUTs mean. How big is this? So this is a graph of the current programmable logic market of a lot of the devices that we could see. And you see your lookup tables on the x-axis, that the more lookup tables is normally the more you can do on the device. And then obviously you have your cost on the y. And if you look at where it compares to other competitors and other FPGAs and CPLDs, it is significantly cheaper at that low end. For only $1, 32 lookup tables looks to be a bargain. Other devices that have similar lookup tables can be $2 or even $3, which if you're doing large production runs, that can really start to add up. If you need more functionality, we have this FPGA portfolio that you can use and incorporate into your design, but then you just are going to have to pay a little more for that functionality. We're hoping for designs that need a little bit more than CLCs can offer, but not quite near what full-scale FPGA applications need. The CLB will fit very nicely. And even compared to some of the CPLDs, at that price point, I know there's an ATF device right to the left of the 131 for more LUTs at roughly the same price point. Now, there are still a lot of reasons to use a CPLD. In fact, if you go to the Configurable Logic Block peripheral page or microchip.com, we have an article that talks about when you're going to want to choose a CPLD over something like the CLB. There are still many advantages to using a CPLD, but depending on what you are designing, CLB might be the way to go. So I recommend you go and read that article if you are wondering, should I use CPLD or come over to CLB?
So if you need something a little bit more complicated, you want to look at something like some of the igloos or the Pro ASICs and stuff like that.
One of the places that they do very well is when you need a lot of IOs. If you need a lot of inputs to be monitored to go to an output, igloos are the way to go. The CLB only has, I believe, 4 to 8 inputs depending on how you configure it. If you need 20 plus, I recommend paying a little extra for that igloo, and then you get a little more speed as well.
Okay.
But so that's the market. So let's look at what you can do now with this CLB that you have.
But before you get to that, there's something I want to speak to here. You hit on two key points in development. As a engineering firm, these are things that we run into all the time because we work with large customers as well as small customers on a regular basis. And we find that the small customers, their development process is of course driven by time to market, that's really important, but also non-recurring engineering cost. And so every time you have to pick up a new tool chain, if you have to pick up a new device, it can add dozens or even hundreds of hours to the development cost. And that can be expensive because it's hard to amortize over a medical device or a military application that might only be producing a few thousand a year. But on the other side of the spectrum, you've got the unit cost. When you're talking about consumer applications, you're doing hundreds of thousands or millions of units a year, that's when you want the unit price to be down. But you also, with your products, get the benefit of the lower development effort and the lower unit cost because you're able to pull so many different, what would be otherwise different peripheral chips into one package, especially for simple consumer products. So I just wanted to make it clear to the audience how this is kind of like a two-punch kind of approach to things to get something into such a small, low-cost chip with one tool chain, one development process.
You're exactly right. I couldn't have said it better myself. Looking back at this graph, for those large, multi-million dollar, multi-million unit production runs that are massive, where per unit cost is the driving factor, we are very competitive in that space. But we also want to make sure we are touching on customers who are doing smaller production runs where time to market is the driving factor. And that's what we wanted to show with this demo.
And that's where we're driven by the engineering cost and the time to market. Right?
Engineering cost, time to market, not having to pick up another device, another data sheet, another tool chain that adds just more complexity and more potential problems.
Well, there's another advantage to having the reduced number of tool chains and the simpler licensing costs. When we're doing medical devices, for instance, you have to have a software bill of materials, and you have to have a lot of documentation on all the software that you used, all the licenses that were involved, and also have a pathway to be able to support that product over the long term. Meaning you have to be able to reinstall all the development tools, access development tools, and if you don't know what the licensing schemes are going to look like, you can have a piece of software that you backed up, and the license expired 3 years ago, and you don't know if they're going to continue supporting that version anymore. And you might be required by the regulatory processes to be able to use that again.
Yeah, and that's a perspective that not many people can think of, but the people that it does impact, it's very important not having to worry about the licensing and extra complexity. Mm-hmm. So yes, looking at what else we can use the COB for. So we had talked about glue logic and CLCs being used at that very low LUT capability, and we're talking about using the 131 in things like interrupting some serial communication and simple tasks like debouncing buttons, LED controls, serial drivers, and state machines. That's in this 32 to maybe 100 lookup table range. At the higher end, we see more, that's when we get into the Igloo FPGA. When people think FPGA, this is where they tend to think of like battery management, camera feed routing, and things that deal with creating UARTs and different closed loop fan controllers. And then just for the sake of completeness, some people, when they think of FPGA, they've only dealt with 220,000 plus lookup tables. We're dealing with high-end ML applications, robotic arm control. And I just wanted to paint the full picture here of what the lookup table space looks like, of what you can do at each level. And we see the 131 at the lower end when you just use the COB and its 32 lookup tables. But when you look at it from a different perspective and you consider the other peripherals on the device as hard IP in the FPGA space, it can punch well above its weight to 500 plus lookup tables. On an FPGA, if you needed to simulate a UART and run a UART on your device, that might take 200 plus lookup tables, but we have a UART module on the 131 and that can interface with the COB. Same with maybe a timer or a PWM generator. Using the other peripherals and interfacing them with the COB lets it punch well above its weight into that 500 and even 1,000 lookup table space for functionality.
And not only do you get those peripherals for free, you don't have to write the code for them. You
it's
don't
integrated.
Have to
Yes,
write the Verilog
yes,
or the
I'm glad you get it.
To make them happen.
That cannot be understated, the ease of use that comes with it. In fact, we're going to see Clifford interfacing with the timer, and it's going to be completely seamless. I think it's a click of a button, and he is interfaced with it, not having to download IP block and then load it in and then incorporate it into the rest of your design.
Nice.
So I'm sure you've dealt with that a lot during your time in
Oh,
development.
too many times.
Yes, there's pain behind the eyes on that one.
Oh, yes.
So that's a space of what the COB can be used for. Now let's look at, we've been talking about this tool chain that's easy to use. Let's give a look at what we're talking about when we say easy to use. This is a GIF of the COB synthesizer running. It's a drag and drop interface that uses a layer of abstraction to pull different signals into and out of the COB that can pull from anywhere on the microcontroller, whether it's an I/O line, a different peripheral, or even the core itself using a register. And then it has a bunch of different features that we hope FPGA designers appreciate, like it supports Verilog for those who are more comfortable with that approach. And then when you synthesize, there's an easy graphic to see, okay, how many lookup tables am I routing through? Can I do a bit of manual timing computation of this? I know how long it's going to take to, I know if I'm routing through 3 BLEs and it's going to take so long to get through each one, I get a rough idea of what speed I can operate at. So there's the COB synthesizer that we've launched, and it's great to talk about it, but I'd rather look at how it's actually used and let you guys see how easy it is to build something using the COB synthesizer and our end-to-end toolchain. So to do that, I'm going to pass it over to Clifford and Ulysses with their demonstration.
Thank you guys very much. All right, so our demo is 2 different traffic lights, as you can see on the desk. We have 2 very important drivers over here. Before they can get to their very busy days, we need to make sure that the traffic lights are giving them information that keeps them safe and makes sense to them. Over here, we have a box with 6 different buttons, 3 inputs to correspond to each stoplight. But let's say somebody messes up and does 2 greens. Well, that wouldn't be safe, so we're going to be making use of the CLB to ensure that everything that gets to the actual drivers and the stoplight makes sense. And I'm going to pass it over to Ulysses to show the synthesizer.
Alrighty, and we're using the CLB to program the hardware because it is safer for a safety critical application of this traffic light intersection. Now let's get started. And like Josh was saying, the CLB synthesizer is available both as an online tool and integrated with an MP Lab. I'll be using the online tool, and then I will be importing that file into MP Lab for this demonstration. So this is the home screen. Here you can see there's a getting started video, some example projects, code examples, anything you might need to help you get started. So let's start with a blank design. And then right here, if you go to Documents, here you can create a new schematic or a new Verilog page. So whatever you might need, whatever you prefer, we have those 2 options. So for our logic today, we're going to use 2 schematics within 2 modules within the main one. So the first one, I'm going to label just light for 1 traffic light. And then I'm going to create another one, and that's going to be 2 light for the 2 traffic lights.
So right now you're creating sub-modules that can be used within your main design.
Yes, that is correct.
So that you can reuse them.
Yes, and then right here on the right side, everything's easy, drag and drop. I'll quickly delete that. If you go down here, the modules will show up on this part right here, and they'll be updated as I add on to them. So for example, let's create just the 1 light. For the 1 light configuration, we want the traffic light only to respond if there's 1 colored light on. We don't want the green and yellow to be on or the red and yellow to be on, just 1. So we're going to have 3 inputs for red, yellow, and green. I'm labeling these as off-sheet ports because these are ports that are going to be integrated into another schematic.
Because it's a sub-module.
Yes, correct. That's going to be red. It's going to be yellow. And then green. Oh,
We're doing it live.
there we go. Let me just redo that. And then this will be green. There we go. And in order to achieve this, we're going to use an XOR and a NOT gate. And at the end, now put, this is going to be error. So the error will only trigger if there are 2 lights of the same color on at the same traffic light. So just like that, easy drag and drop, I finished the first module.
Cool beans.
I'll be working on the 2-light module and the main one as Josh continues, and then we'll come back and I'll explain to you guys what I did.
Okay, so just like that, we saw how you can create a submodule to check if for one of the traffic lights whether or not it is only one light on at a time. Now you're going to go ahead and create the logic for making sure between the 2 lights there are no errors. They don't have the same light on at the same time.
Yes, that is correct.
And then add a little bit more logic. So while you work on that in the background, while everyone can continue to watch, Patrick and I will explore some other applications that we can see the CLB being used in and the ways we've seen it being used in the past or that we think might inspire you in the 2025 Configurable Logic Design Challenge for your own. Hopefully you can relate to one of these applications or think of a way to extend it for your own gain.
I don't know, Josh. We might need to talk pretty fast. This is looking pretty easy. They might get that pretty quick.
Okay, then let's get started.
Go, go, go.
Okay,
Got a
so
race.
on my screen, you see one of the designs that we've actually used internally with the CLB. This is a board that was designed, I think, 20 years ago that used 12 discrete logic ICs to communicate with the larger system for some time. And it shows, it has 6 7-segment displays, as well as taking inputs from a button, taking a bunch of button inputs. And we were able to condense that all into a single PIC16 F131. The CLB was dedicated to driving these 7-segment displays so that the CPU is unburdened with that. And then we were able to use the ADC, the 10-bit ADC, and a resistor divider network to read from the buttons, and then use the using the 131's on-chip serial communication protocols to communicate with the larger system instead of having to use the parallel interface that existed before. And so this was a great application that we were able to condense and reduce our bill of materials by upgrading the technology. And I think that's sort of the quintessential idea of the CLB. Take existing designs that have previous glue logic that have been built in the past and upgrade them, bring it into the modern age. So that's one example, but let's look at a more external example, something you might see in your day-to-day. So we're here in Chandler, Arizona, and so there are a lot of solar panels out here, especially on residential houses. So we wanted to see a way that can we add the CLB to these solar panels. Traditionally, there are 2 ways to do solar panel architecture. You can use a string inverter where all the solar panels are chained in series, and then there's a final large inverter that translates the DC current into AC to connect to the grid. Or a more modern architecture is to use microinverters, where each solar panel has its own inverter. These systems obviously are going to need some sort of safety system to protect from faults if there's a short circuit or 2 wires touch. Or one comes disconnected, you're going to want to be able to enter a safe state. For the string inverter, this makes sense to use traditional CPLDs because there's only a single node. You may want to pay for a little extra speed, and it's all closely connected at a junction box, so you can run direct wires between maybe the CPLD that's monitoring for safety and the larger system.
Hey, Josh, it looks like we've got a question from the audience, so why don't we address this real quick?
Let's do it.
So we've got a question on the YouTube chat. Are there coding best practices suited for CLBs and for Verilog with these devices?
Let's see, coding best practices. There are proper design architectures on the configurable logic side of maybe the best way you want to do it. I know if you've only dealt with Verilog from a college level, a place that trips a lot of people up is the simulation versus bringing it into hardware aspect of it. The CLB synthesizer uses Verilog 2005. So if you want to ensure everything you're going to write is going to work perfectly on the CLB, I recommend reading up on that. There's also a how-to guide. If you go to either the landing page that you saw on the CLB synthesizer earlier, there is a user guide to help give some guidelines and best practices when using the CLB.
So I think what I like about the tool environment is that, yes, you're drawing a schematic or you're kind of creating some Verilog code. It's pretty well constrained within the Microchip environment. You've got kind of the hand holding on both sides of things for the basic configuration of the hardware, and then you can just kind of work in your own sandbox for the configuration.
Exactly. Yes, that's exactly right. And we wanted to keep it within that Microchip ecosystem because when you're interfacing a CPU with a programmable logic device, a lot of things can go wrong. And so we have a software in register to feed directly from the CPU into the CLB and make sure there are no technical glitches. And so we've kind of handled that because it's buffered in the register, that things should be fed in a good fashion, so there's not too much you have to worry about from a coding perspective of your core.
Awesome. Yeah, and certainly any of you online, if you have questions, now's a great time to be asking them. And of course, you know, if we're not answering them as well as you'd like, please ask a follow-up question. We'll try to get to them if we have time.
Good, yes. We want this to be as interactive as possible so that if you feel like entering the design contest or using the CLB, we want you to hit the ground running and not be left scratching your head. So jumping back into this example, if we don't have any more questions, I was talking about how string inverters often use CPLDs because there is a larger current required, but these new microinverter use cases, that's a great application for the CLB. You can be using the PIC16F131 to communicate back to the central node using its communication protocols, but then the CLB can be dedicated to watching the power, the temperature, the current, and the voltage of each of these microinverters to make sure that they are safely monitored. You're not going to leave the safety monitoring up to code. It's in dedicated hardware with nothing interrupting it to give that peace of mind, especially if you're going to put solar panels on your house. It's great if it can have a dedicated monitoring device.
You know, I think there's some really interesting subtlety here about what you can monitor and what you control. One of the neat things about this is when you're dealing with high power applications, when there's something not quite right, a current's a little bit too high, a voltage a little bit too high, or a current is too high while a temperature is too high, you can have a lot of edge cases that can destroy your product, or maybe even cause injury in the wrong circumstances. And being able to monitor those things at high speed without chewing up a whole bunch of processor cycles is really appealing, because it can greatly allow you to reduce your margin of error and tighten up designs, further reducing cost. So for instance, you might have a MOSFET that you're trying to keep in its safe operating area. So because once you're out of the safe operating area, they obviously can melt down, they can explode, they can stop working correctly. And you have to have enough boundary on that to keep things safe and operating properly. The faster you can respond to your MOSFET starting to get out of that safe operating area, the more likely you are to keep it from getting damaged, meaning less warranty repairs, less product issues, and potentially tighter requirements on your product design, reducing cost, allowing you to use lower complexity components.
For me, it's the peace of mind that comes with the dedicated hardware. While you can feel you're confident that your microcontroller with the code is going to be able to respond fast enough, it's not guaranteed. The reproducible latency that comes with programmable logic devices, it's going to execute in the same speed every time. It cannot be understated. I couldn't agree more. We can even dive in a little more on this and see a more fleshed out example of what this might look like, having the CLB doing dedicated monitoring.
Yeah, so this is exactly what I was kind of talking about here is, we did some applications in the past where we were working with, some of those really gigantic IGBTs, those big giant brick things. And I tell you what, man, when those things explode, it's like a shotgun went off. You do not want to blow them up. And we've done some applications where arcing and shorts on the output of a power supply are very, very common. And under normal circumstances, this kind of behavior could easily blow up your drivers, they could blow up your MOSFETs. But if you design for it and you can respond fast enough, you can actually keep your MOSFETs and your MOSFET drivers in a safe operating area and not explode. And it's all about monitoring the right signals, obviously voltage, currents, what portion of the waveform that you might happen to be in, what the operating conditions are. And if you can monitor those fast, you can often shut down those gate drives, remove the energy from the system before software would have been able to take an effect.
Yeah, and you raise a good point of designing it and thinking about this in the design phase is very important. Even if your core is running, having the thought of, okay, I might need a little bit more speed for these signals just to be 100% sure, or as confident as I can be that I'm going to be able to respond in a timely manner. I know the CLB can run up to 100 megahertz.
Wow, that's pretty fast.
Very fast. And so for these examples where IGBT needs to be shut down properly, the 32 megahertz of the core versus the 100 megahertz of the CLB, that difference can be save you from that shotgun blast of it exploding.
So that kind of reminds me of some of the low power applications again. So tell me if this is true or not. When you're doing a low power application and using the CLB, can you keep the CLB responding and running fast while having the main processor core running at maybe just a few hundred kilohertz?
Yes, you can clock
Really?
them using different oscillators.
Oh, that's super interesting.
The
So you
core
can
can
really
be-
drive that power down.
Yes, the core can be running super slow, or it can be completely off, and the COB can continue to operate.
So you can do the really, really fast, snappy monitoring with the CPLB at low power, and then when you actually need to do some processing, presumably less frequency, you can wake up the processor, maybe go a little faster, and then slow way back down again.
Yes, exactly. And that's how we were hoping it to be used, by integrating them. It's hard to add that nuanced interaction between the two if they're not seamlessly integrated into the same device.
Cool.
Yeah, and it's great when you're using it in these monitoring applications where you're having CLB doing safety monitoring. I know we've looked at solar panels, but even on more simple applications like a battery charger for your car, a lead-acid battery charger, if you want to be following a charging algorithm and you just want to connect it to your car when you realize it's dead, that can be great, and you can sell a consumer product to do that. But sometimes when I wake up in the morning and my car is dead, and I'm just groggy and I just want to connect it, sometimes if I connect it backwards, or if I'm using it for a different application and connect a 12-volt charger to a 6-volt battery, I want to know I have peace of mind that there is protection built into my product, that it's monitoring the temperature, the pooled voltage and current, and being able to shut things down if I mess up as an end user. And so having dedicated hardware cannot be understated for that.
You know, speaking of dedicated hardware, it makes me think of safety critical applications, especially in medical devices. And Ulysses kind of mentioned this in passing before. There is a significant advantage, it turns out, to keeping as much out of software as possible and moving a lot of your safety critical functions into hardware and into dedicated logic. I don't know how many of the audience knows this, but software safety is one of the biggest requirements out there these days for regulated products. And it's one of the biggest concerns that the FDA has, because software has so many different inputs and so many different outputs. It's much more difficult to go through all the different permutations of possible testing versus programmable logic or dedicated hardware. It's much easier to prove inputs and outputs. Most of the most serious harms that have happened in medical devices over the last decade have actually been software related and not hardware related. So there's an industry push to keep as much safety critical functionality in hardware as possible. So when you have the opportunity to use something like a CLB to handle safety critical functions, like maybe a good example is a medical laser we did for LASIK eye surgery, and we had to monitor the energy output. You weren't going to hurt someone if your energy was too low or the frequency wasn't quite right, but if your energy got too high, you could really damage someone's cornea, and you don't want to do that. So we actually had separate logic and separate watchdog circuitry just watching some op amps for the total energy output. And that could have all been incorporated into the CLB to monitor the safety functionality, while the more complicated software in the microprocessor could handle the user interface, the user experience, monitoring temperatures and other aspects of the system.
Wow, yes. Well, I got LASIK a couple years ago, so thank you for keeping me safe and designing
I'm
that
glad
in so
both
that
your eyes work
I can
still.
see today. Yes.
Yeah, glad I could contribute.
Let's look at one more example before we throw it back over to Clifford and Ulysses. I know we've touched on safety a lot, but let's look at more proprietary things. Maybe not safety critical, but let's say you want to add a proprietary feature or functionality to a design. Normally, you can go out and buy an ASIC if you want to do something for protocol conversion or adding standard features to a design. But if you want to extend that ASIC, there's not a lot of options out there besides programmable logic, FPGA, CPLD, and that's going to add to the bill of materials. You're going to have 2 chips, so there's more quiescent current. But if you're able to use the CLB to extend this functionality, it can make your life a lot easier. So for example, here is we're adding two bits to the RC5 protocol. Or if we wanted to, let's say, invert RS-232, we can just take in the UART module, add a NOT gate, and then feed the proper signals into the UART or SPI to slightly modify it that you wouldn't be able to do with an ASIC. So you don't want to have to bit bang this or get that custom ASIC. The CLB is a great way to do it because you can just tweak an existing protocol and couple it with the UART, I2C, or SPI hardware modules within the CLB to make life a lot easier. I don't know if you've ever experienced anything like this where you had to tweak a protocol, but I know it can be a nightmare.
Yeah, actually, we've had this exact situation. So we were working on a military program that had this really weird old IBM serial protocol from 1970. It was called SDLC, and you could get protocol chips that would do SDLC to SPI, and they were $100 and out of production. And so our only option at the time to do a custom serial protocol like this was to use a CPLD. We used a fairly lightweight one, a Mach X02 from Lattice, and we had to learn the tool chain. We had to do a bunch of schematic work in Verilog. We're C guys, we're C programmers, we're embedded guys. So having to write stuff in Verilog was a hassle. It took a lot of extra time. And not only did we have to write the SDLC protocol, but we also had to write an SPI protocol because it needed to talk to our main DSPIC microprocessor that was running the whole rest of the system. So to have been able to write that SDLC protocol, which wasn't complicated, but it was certainly unique, and you couldn't do it bit banging because it was fairly fast, to be able to have done that in a CPLB instead of into a separate CLPD would have been really, really nice. It would have saved us quite a bit of development time and would have reduced the cost on the application.
Well, it's very good to hear all of these places that the CLB could have been beneficial. And we're hoping that's what people are seeing online, is they can think of examples in their engineering career where having a CLB would be beneficial.
So we got another question from LinkedIn online. You want to address that, Josh?
Sure, let me
Here, I'll go ahead and read it to you. So when you turn off the core and let the CLBs clock at full speed, how does the system handle isolation and level shifting requirements coming from ASIC? This person's coming from an ASIC low power background.
So I assume what they're asking is, when we have the core off and the CLB is running, how do they know when it doesn't become a voltage level high and a voltage level low? That is how I'm interpreting your question, and those should be spec'd in the datasheet depending on the operating voltage that you are running at. If I misinterpreted your question, please feel free to clarify it, and I'll be able to give you a better answer in a bit. But let me throw it back over to Clifford and Ulysses to see what they have done while we've been talking about applications.
Alrighty, so when we start out, we just built the one traffic light intersection for the intersection, and that was this schematic. And then this module, I inputted into the two traffic light intersections. So we have our 6 lights right here on the left side, and we are trying to prevent errors. We're trying to prevent, well, legal intersections. So
Trying to prevent legal intersections?
we're trying to prevent them from crashing into each other. So basically, red is legal, green, yellow, or any combination of those are not legal. And so we use an OR to signify that, and then an AND. So any combination of red and yellow should give us an error, as well as any combination of red, yellow, or green. There's more than one color on one traffic light.
So this 2-light checker schematic essentially is saying if both stoplights are saying go in any shape or form,
Yes.
or if there's an error on an individual light, flags an error.
Yes,
Gotcha.
that's right. And then for our main, I combined everything together. So on the left side, we have our 6 buttons that we control to light all 6 colors on the 2 traffic lights. And on the left side, we have the outputs of what the traffic lights actually say. And to do that, we use our 2-light traffic checker. So I inputted all these into the 2-light, and then I used AND gates to prevent the color from showing if there is an error. And if there's an error, I used a timer, so created a timer module right here. It's a series of flip-flops to slow down the clock and so we can create that pulsing yellow light.
Makes sense.
Yeah.
And so for the timer, you had 4. So I believe it divides whatever the clock speed is by 4.
Yes, that
And
is correct.
Through
here.
testing in the past, we sort of found that gave us the speed that sort of mimicked what we would expect from a traffic light
Yep.
flashing.
And as well as some other settings in MPLab, that's what we came up with. Yeah.
I can't believe you guys got that whole application done in 15 minutes. That's pretty impressive.
It was
You
fast.
guys are speed coders.
Practice, I guess. And then these we use an XOR at the very end for our yellow light outputs right here. So that's if there is an error, we want the yellow to flash. So we want there to be an output of yellow flashing.
Makes sense.
That's basically it.
And I have one more question. For
Yes.
your inputs on here, they're a different color from the ones that you were doing previously.
Oh, yes.
What is the difference?
These inputs right here?
Yes, sir.
Yes. So our microcontroller has 4 direct inputs, but because we have 6 buttons, we're using digital inputs that we're going to map out in MPLAB to the pins that we want to use.
Makes sense.
And so we used CLB Win 0. There is 32 of them, but we just needed 6.
So
And-
this SWIN is that software in for the core to interface with the CLB that we were talking about earlier.
Yes, that is correct. And then for the outputs, I just selected the first 6 of them. So PPS out 0 all the way to 5.
So you have 8 outputs, but only 4 inputs. One note I'd like to touch on is if you wanted to do this design without using the software in and keep it entirely in the CLB, this is one great application of the CCLs. We weren't sure how many pins to assign to what for this device, so we put 4 directly from the IOs, but if you want more IOs in, you can route an IO to the CLC and then straight to the CLB, and that way we can cut out the software in. For this demo, I think we found it was just easier to do live if we use the software in, so you can see the end-to-end toolchain of how to access different aspects.
Yes, that is
Makes
correct.
sense.
Alrighty. So then at the very end, I'm going to download it and then mail it to Clifford. So I'm going to save design. I'll label this, let's say, USA traffic light.
Perfect.
There you go. Okay. So that's saving. I'll send it right over to him.
And then we're
Okay.
going to trade HDMI cables. So
Yes.
it'll take a moment for you guys to see my screen. But once you do, you will be greeted to a blank and empty MPLAB X file. And here's hoping.
One thing I'd like to touch on while we're in the interim, I know you guys are going to show us how to use the CLB synthesizer within MPLAB, so it's an end-to-end toolchain. But for those of you who don't necessarily want to use Microchip Code Configurator, our graphical configuration tool, within the online web service, you can synthesize and download the synthesized bitstream and just include that in your project files. There's a how-to guide download, but we wanted to leave as many options open to if you only want to use the CLB synthesizer online and don't want to touch MCC. But we find MCC is much easier for integrating with other peripherals and setting up the IOs, so that's the way that we're going to be doing it here.
Yes, sir. All right, and here we go. So I've named our blank project CLB_traffic_light. I have already opened MCC. Like Booth mentioned, it is our code configurator. It's going to generate all of the code for us, except for a very small bit, which I will be writing live. So I'm going to click on Resource Management, and this shows us the same sort of information that we see in the center of the screen, which is all the different peripherals that we have access to on this 131 chip. I'm going to be adding 2 peripherals in here. First is the CLB, and then the second one is Timer 2. Timer 2 is the thing that is actually going to be giving the information, or giving the cadence for our flashing yellow light. All right, so I'm going to change the clock source to our low frequency oscillator, and then I'll also be changing this time period to 0.001. And once again, that was just something we found through repeated testing, just making sure that it didn't hurt our eyes and sort of made sense. So that's all we have to do for Timer 2, which is pretty cool. Next up, I'm going to open up the CLB. This looks fairly similar to what Ulysses was showing on the online tool, and it is genuinely the exact same thing. I'm going to click Load, and then I'm going to go to Desktop. I put it in CLB Live right here, and then USA Traffic Light. Cool. And then we have everything that Ulysses just did online, which is pretty nifty. I'm going to make this a little smaller, and then I'm going to click this Synthesize button, and then this should hopefully tell me that everything is groovy, and we're good. And I believe we're using 28 of the 32 lookup tables, which is pretty nice that we're almost maxing out the CLB with this. All right, so now that I have synthesized it, I can click on the pin grid view, and this will now update to reflect all the CLB SWINs that Ulysses put in. Now, I've already wired our project to make our lives easier in the software section of it, but we're going to start with port B4, and then I'm just going to go down in a line like this. And then that will give us our 6 outputs. And then as far as inputs, 1, 2, 3, 4, 5, 6, I can count, that's amazing. For our inputs, I'm going to start with the next available pin, which is RC2. And then I'm just going to count down 1, 2, 3, 4, 5, 6. So now we have all of our pins assigned to whether or not they are inputs and outputs. Next thing I have to do is actually name them. So I'm going to go back to Application Builder and double-click this pin right here. Oh, right to the side. And then I'll be able to name everything. So they give you names right off the back. I'm going to change them to be a little bit more readable when we're writing in software. So for our inputs, I'm going to name them I, and then whatever the first letter of the color is. So for this output, I'm going to say O, R1. For this one, it is R green, so that'll be OG1. Next one will be yellow, OY1. And then we're going to get to our second traffic light, so OY2, OG2, and then OR2. So that was all of our outputs. Now for our inputs, I'm going to go to I. We're starting off with red 1, so R1.
So while you do this, Clifford,
Yes, sir.
one of the reasons that this is a necessary step is because it's a feature within the 1 through 1. So the COB and the PIC16F 1 through 1 uses peripheral pin select, and that lets you route any I/O pin to any peripheral. So one of the advantages of that is you're able to reroute your COB configuration on the fly. If you want to be running one thing and then you hit some condition, you can have the core load in a different COB configuration and have the pins do something completely different. So what we're seeing in MP Lab right here is that layer of abstraction of how do we interface what we assigned abstracted pin 0 in the COB to a physical pin on the device.
Yes, sir. All right, so for our logic, we are expecting a high signal to trigger one of the lights. If we were doing ground or a low signal, I would be making use of these weak pull-ups within our MCC. But because we are expecting a high, I have soldered resistors to the back of this board. So if you were to try to follow along with this example, you would have to do the same thing. But that brings us to the end of what we're doing within MCC. I'm going to click Generate, and it's going to tell me if there's any errors, but generation is complete. When I clicked Generate, that added all of the files that we need to interface with the 2 peripherals that we added, and it also creates a main file for me to program within. So writing code live always works well, but we're going to see what happens. So the very first thing we need to do is be able to write information to the CLB SWIN register. So we have 32 bits of memory that are dedicated to those inputs. Since we only have 6, we'll only be interfacing with 6 of those bits. But first thing I'm going to do is declare uint 8_t data, and data will be what we are passing. I'm going to make sure that that is 0. Just so that there is nothing floating within it. And then I'm going to declare it as 0 again once I get in here. And this is within our while 1 loop, so it's just going to be going this entire time. Up next, we'll be doing if statements. And so if, and I'm going to say IR2 underscore get value. And so this is a function that will return high or low depending on if the actual pin is receiving a high or low signal.
And where does that function come from?
From MCC.
It's something that it gave you to use.
Yes, sir.
Is there a way I can see all the functions that it gives me?
100%. So if I were to hold Control and click on this, it's going to open up the header file for pins, and essentially it shows you what it is doing. And it's not only for the pins, this is for everything that MCC gives us. So if I wanted to do something for the CLB, which I will be pulling up later, it'll also show you all the commands you can do with that as well. Back to our main. So we have an if statement, but we're only going to be doing one thing at a time. I want to modify data, and I'm going to OR it with 1. And so 1 in binary is as many zeros as you want, and then 1. And that also corresponds to the first bit that is assigned to read to output. And so by ORing them, the only thing I am modifying in the CLB SWIN memory register is that single one that is responsible for that output. I'm going to copy this so that our lives get a little easier. And I will fix formatting in a second, I promise you. And then I'm going to do one final copy of these 3, so that'll have the 6 that we need.
Actually, while you finish this example, would you mind Patrick and I talking through one last application for the CLB?
1000%. Go for
Okay,
it.
so while Clifford finishes up the code and just puts the polishing touches on it, I want to look at, we've looked at using the CLB for safety, we looked at using it for extending functionality, and now we're going to look at using it for speed. So this is a theoretical application for using the CLB to do Manchester encoding. There are a bunch of ways to run different wires, but in this example that we're showing here, we want to communicate between 2 nodes. We can run a bunch of power and data lines to both power them and communicate, but if you're running long runs of copper, sometimes it's cheaper and better to just use one pair of wire and then use smart intelligence on either end to send the data over the same lines as power. And that's where you get power over data lines. So a single wire pair gets both the power and the data. However, when you do this, there's a little bit of complexity added. You need to ensure there's data integrity, so you need to add a layer of encoding to make sure the data gets from one end to the other. Manchester encoding is a great way to do it. It synchronizes the data, it detects the errors, and there's no polarity reversal. However, everything has a cost. When you encode data and add Manchester encoding, you either are going to need to let your core be sitting there and doing it, or you're going to need to add an extra component to your bill of materials to do the encoding. We were able to find if you use the CLB to encode the data, it can actually encode it so fast that you can reduce other components in the system. For power over data line, if you encode the data quicker, you can actually reduce the passives because there are smaller common mode chokes, and that gives you, not only are you saving money on the components that are actually doing the encoding, but also the components that are supporting the power over data line. So overall, by increasing the speed through the CLB and offloading the CPU, there's no extra cost to the BOM, and you can reduce the end-to-end system rate, which has smaller and cheaper passives.
So Josh, it looks like we've got another question from Mark O on YouTube. The question is there an SW out register like the SW in register on the CLB?
There is not. There's not currently an SW out.
Why not?
There is not an SW out.
What does it do? What is the SW out and SW in? What would those be?
So the SWM be software in, that lets you pull data from the CPU. There is
gotcha.
a debugging register of SW out, where if you want to pause and go and debug the CLB line by line and look at what the contents are, theoretically yes, but there is no SW out at this time for the CLB. So you cannot take data directly from CLB into a register.
So I've got my own question for you, actually.
Okay.
I want to know where I can get a dev kit right away because I want to win this design competition. I want that $10,000.
That is a great question. I'm so glad you asked. If you go to microchip.com and just look up the PIC16F 131, there is a Curiosity Nano. That is the dev kit that we will be shipping people. They should be stocked in DigiKey and Mauser, as well as Microchip Direct. I recommend picking one up and just start tinkering around with the CLB.
I'm going to get a whole team of people working on this design competition.
I bet you're going to buy them all, so we're out of stock. But I highly recommend getting it and start tinkering around because there's so much you can. It's kind of fun to play around, and I know I've always shied away from programmable logic and stuck to the microcontroller side. So this was a nice foray into a completely different side of the computing space.
Well, it's cool when you guys have a new product like this. It'll be really interesting to see what clever ideas people come up with and novel ways to use this that nobody's thought of before.
Yeah, I'm really curious to see what some of the brilliant engineers out there have to do, and I'm sure I would be blown away. I've been racking my brain for months now thinking of all these cool applications that we can use it, but I'm sure industry experts are going to humble me. So with that application, let's throw it back to Clifford and check out his finished code and the final example.
Yes, sir. All right, so on my screen we have the finished code. As you can see, these are all just the powers of 2 because we really only want to affect one single bit of that register at a time. But after that, I have the CLB1 swin write 8. They have write 16, write 32, but because we're only dealing with 6 bits, write 8 is totally appropriate. We're passing data to that function, and then I have 2 buffers, no-op, and then I also have a very tiny delay. I probably don't need both, but it makes me feel more comfortable, so that's what we're going with. And that is genuinely all it takes, and now is the moment of truth where I'm going to program my device and see if things work, so let's go. All right. So let me click on that. Devices programming, I'm going to ground my two LEDs, and if everything is correct, since we have no inputs currently on, we should see flashing yellow lights.
No smoke.
No smoke,
No
and we got
smoke.
flashing yellow lights. All right, just to cycle through all the different inputs to show everybody that it works, let us take a valid input as 2 reds, and we should see 2 reds show up. Let's say a red and a green. We have a red and a green. Red and green the other way, and we have that going for us. What about 2 yellow, something that we don't like? And we got flashing yellow.
And that's the error state.
And that is the error state, thankfully. If we were to do multiple lights selected on a single one, it doesn't let that go through either. And so as far as I'm concerned, we did it live and it works. We sort of modified this example from something that we have currently on Microchip Try. I'm going to make sure that there's a link in the chat for that if you guys would like to read the application note that we based this off of, or if you just like to follow it along at home. And I hope that this inspired you guys for the Microchip's Configurable Logic Design Challenge, and I wish you luck. But back to you, sir.
Yeah, one thing that I mentioned, Microchip Try is our online platform for being able to interact with these development boards and different various hardware live. You can actually reserve the hardware and be able to tweak it yourself. The hardware is live, you get a live video feed, and it lets you interface with the board without having to purchase it and wait for it to get shipped to you. So it's at try.microchip.com, and if you ever wanted to tinker around with some boards, I highly recommend checking it out.
So is that's a free service offered
Free
by
service.
Totally
Microchip,
free.
where I
Offered by
can
Microchip.
actually simulate, execute, and work on real hardware. Where's that located?
So
Is that-
it uses pre-built examples live. So for example,
okay.
we're showing a traffic light. I know we show some features of our op amps and ADCs to reduce noise. We have one with some IoT examples for a clock. We have one that shows off our DMX protocols on our PIC18 microcontrollers. And it just shows various ways that you can do things with our
Oh,
microcontrollers
okay, gotcha.
and how our features really give us a step up on the competition.
Got it. That sounds really interesting. I'll have
It
to
is.
check that out.
So that's all that we have for you today in terms of knowledge to share about the CLB. If you have questions about the design challenge or really any CLB questions in general, you can email us at clbdesignchallenge@microchip.com. If you want to learn more about CLB and check out examples, if you go to discover.microchip.com, we have a bunch of examples, full code examples and write-ups that we didn't talk about today that if you get your Curiosity Nano for the design contest and you want to just load it up with something to see that it's working, any of these examples will work. I'd like to thank Patrick Marcus for joining us today and providing a lot of very valuable knowledge.
Yeah, certainly if any of you out in the audience are interested in working with any of these Microchip products, or you have a product development challenge that you don't quite have the resources for or the knowledge for, we're always happy to help. As you can see, we're really friendly guys.
Good, and I wouldn't have it any other way. I wouldn't have any other 3 people to educate about the CLB with.
Thank you very much.
All right, well, that is all that I have for you today, so I appreciate your time. And once again, reach out to us if you have any questions. Take care.